Hello everyone, this is John Ferguson with the Appalachian Search and Rescue Conference and the developer of Integrated Geospatial Tools for Search and Rescue, or IGT for SAR. IGT for SAR is an extended adaptation of the popular MapSAR map template that runs in ESRI's ArcGIS for the purpose of managing wilderness search and rescue operations. IGT for SAR focuses on automating the workflow of tasking and managing search and rescue field teams, as well as providing a variety of analytical tools to assist in prioritizing the search area. I should note that while IGT for SAR was developed with wilderness search and rescue in mind, it is also applicable to various aspects of law enforcement and homeland security. Although IGT for SAR is free to the public and open source under the GNU General Public License, it does require ArcGIS, and it works with versions 10.0, 10.1, and the new 10.2. In this video, I'll provide a brief overview on the use of GIS for search and rescue and the functionality of IGT for SAR. Soon to follow will be a series of video tutorials, each detailing some aspect of how to use and make use of IGT for SAR. So with that, let's go ahead and get started. Search and rescue is an inherently spatial problem, both from the standpoint of managing personnel in the field and understanding how the environment influences decisions made by a person that is lost. The map has always been at the heart of any SAR operation, be it a topographical map, an area map, street map, or even a hand-drawn sketch. Because SAR operations often deal with large geographical areas, we need to be able to visualize the entire search area beyond our immediate visual boundaries. Maps not only provide a bird's-eye-like view of the terrain, but allow the user to better understand the environment that they're working in. Through this understanding, we can reduce the risk to searchers and more effectively manage resources. Maps also allow us to better communicate information to others, such as family members, the media, other searchers, or the responsible authorities. Because maps have been an integral part of wilderness search and rescue, over the years, we've developed a workflow that is recognized and endorsed by most, if not all, nationally recognized curriculums, and is centered around the map. The classical approach to managing SAR operations consists of placing a number of acetate overlays, or transparencies, on top of the map and recording various information on each respective layer. Layered information may include the initial planning point, such as the last known point or the point last seen, search segments, unmapped terrain features, clues, etc. Those of you familiar with Geographical Information Systems, or GIS, may actually see this as a sort of manual or non-digital GIS. At the end of each operational period, the overlays are removed and stored and new ones are placed on the map. This prevents clutter, as this manual process of drawing features does not easily lend itself to hiding information or turning off layers. Some information may be transcribed onto the new overlays, but typically, if someone were want to examine data from previous activities, they would need to go through the process of reapplying the acetate overlays manually. Not only is this a very cumbersome process, but it basically guarantees the separation of spatial and non-spatial information. For example, in drawing the initial planning point on an already crowded acetate overlay, why would you write in specific information about the subject, or even note that the IPP, or that initial planning point, is not the official trailhead for a given trail? There just wouldn't be room to record non-spatial attributes for each spatial element. This results in relevant data being stored in multiple locations, maybe some on the map, maybe some on a form stored somewhere else, and thus not being readily available to assist in dispatching teams or conducting an analysis of the situation. Because paper maps are static, their information can quickly become outdated. A static map may show the absence of a road when in fact a road exists, and this information can be relevant to both the search teams and the subject. And finally, paper maps do not lend themselves to allowing users to truly interact with the data. Yes, we can interrogate the map point by point, but some terrain analysis, as we'll see, requires us to explore the entire surface, or attributes that are applicable across the large surface, such as land cover or elevation. Geographical Information Systems, or GIS, allows the maps to be dynamic, permitting us to combine both spatial and non-spatial attributes to provide a more in-depth understanding of our environment. For example, we can record not only the location of a backcountry ranger station, but also the name and contact information, as well as the work schedule for the staff ranger, allowing us to know if someone was on duty when a subject was reported missing. We can also immediately update the map and even apply corrections. And because we have translated spatial information to ones and zeros or computer language, we can write programs that allow us to quickly interact with the data, thus creating new knowledge or providing a better understanding of the spatial distribution of various features, including the ones that we've added. Because search and rescue is such an inherently spatial problem, there are many opportunities for applying GIS. However, there are some specific needs that must be addressed, such as providing maps for teams going out into the field, or helping us plan and track the progress of search activities, or providing logistical support, for example, by helping us decide where to place helicopter landing zones, or identifying areas where communications could be difficult. And because search and rescue typically involves large geographical areas, we can leverage our understanding of lost person behavior and terrain analysis to help us prioritize the search area. And finally, we need to be able to communicate information to other searchers and staff, as well as family members, the media, and the public. But Wilderness Search and Rescue offers some unique challenges for applying GIS. For starters, we're oftentimes working in a disconnected environment, so we typically don't have access to the cloud for either software or data. And along with data access, it's oftentimes difficult to identify exactly what data is needed. We began with some guidance from the wildland fire community, but in the investigative environment of search and rescue, all the data can be potentially relevant. Thus, not only access of data, but data maintenance and management become an issue, particularly given the search area can be geographically large with sparse data coverage. And finally, GIS usage in search and rescue is only just beginning, so no training standards exist. And we often struggle not only with trying to find users familiar with GIS, but management that understands its capabilities. Folks have been working on applying GIS to wilderness search and rescue independently for some time. But in 2008, more organized discussions began and a working group was formed. This group has now expanded to almost 500 members worldwide, and it's included annual gatherings for the past several years with the intent of standardization. From this working group came a real grassroots effort by volunteers and professional SAR personnel and software developers to produce a pre-formatted map template within GIS to facilitate its use in SAR operations. This included the development of both MapSAR and IGT for SAR. These video tutorials will focus on IGT for SAR, which includes a number of data layers and tools to automate workflows and provide suggestive analytics to assist in prioritizing the search area. This first part of the video introduces the use of GIS for wilderness search and rescue, with the second part offering a brief introduction to the IGT for SAR map template. I'll follow up this video with a series of tutorials on various aspects of actually using IGT for SAR for operational management and planning. This will begin with a description of how to install IGT for SAR and create a new incident template, and will progress through creating hasty or quick response tasks to get teams into the field. And next, we'll expand on that concept by showing how to utilize prioritized search segments to help plan search operations and track progress. And then we'll consider the use of GPS devices and how we can use them to ensure areas are properly searched. But before we really go much further, we need to have an appreciation for the minimum essential data sets required for planning and managing operations. In the next few follow-on videos, we'll explore the detailed aspects of search and rescue planning. This will include an introduction to the capabilities of using GIS for scenario and terrain analysis, as well as historical data to better understand lost person behavior. We will also examine planning with the aid of structured analytic techniques and look specifically at cell phone-related searches. Once we better understand the advantages of GIS, we will consider how to use it to improve our resource allocation and overall tactics. It's also important to understand how we communicate information to non-SAR personnel, as well as utilize mission information to create lessons learned. And finally, we'll explore ways of leveraging technology to allow for more information sharing to persons outside of the on-scene operation. That's taking advantage of expertise from literally around the world. Integrated Geospatial Tools for Search and Rescue, or IGT for SAR, is a map template environment created inside of ESRI's ArcGIS and was adapted from the popular MapSAR template. As I mentioned previously, IGT for SAR is compatible with versions 10.0, 10.1, and the new 10.2. Installing IGT for SAR consists of only a few steps that create a generic template that is used in forming each new mission. At the start of a new mission, the Create New Incident tool is run that allows you to choose which map projection to use, as all that are available in ArcGIS can be used within IGT for SAR. When opening the template for the new incident, you will be presented with a screen that looks similar to this one, but with the projected map, if you so desire. IGT for SAR includes a number of pre-formatted data layers to store both spatial and non-spatial information. To improve appearance, even non-spatial data is stored in feature classes as opposed to tables, thus clearly displaying all the data that is in an easy-to-read and understand format. We'll explore each of these data layers in detail in the follow-on tutorials. A pre-formatted toolbar is also included in the template, and that rearranges some standard tools from ArcGIS, along with some new ones specific to IGT for SAR template. In this first video tutorial, we'll also focus on several add-ins that are used, including the Attribute Assistant and the IGT for SAR config add-in. And finally, at the heart of the IGT for SAR is the geodatabase and the accompanying file structure. IGT for SAR also incorporates a number of tools to assist with workflow automation and analytical functions. These tools are predominantly comprised of Python scripts that have been developed to take advantage of the vast capabilities of ESRI's ArcGIS. To assist with production, IGT for SAR includes a variety of meaningful color coding and standardized symbols. So you begin an operation by providing information about the incident and plotting the initial planning point, or IPP, which is typically the point last seen or the last known point. Various elements are designed to assist and automate the data entry. First, upon creating certain features such as the IPP using a pre-designated symbology, an attribute dialog box appears. And through the use of the add-in Attributes Assistant, some data such as coordinate calculation, feature type, etc. are provided automatically. Additionally, IGT for SAR incorporates multiple static and dynamic domains within the geodatabase. These domains create a drop-down list environment that improves data accuracy and consistency. One of these domains in particular is related to the subject category, as defined in Bob Custer's text on lost person behavior, and is used to support suggestive models included in IGT for SAR that can be used to assist in prioritizing the search area. I mentioned the use of various Python scripts, with one of those scripts providing immediate creation of a missing person flyer using data stored in various attribute tables. Once you've identified the initial planning point, we often want to quickly get teams into the field. Using a combination of the Attributes Assistant, geodatabase domains, and Python scripts, I provided a scheme for quickly generating hasty or quick response tasks. By creating a hasty point, line, or area, the user is presented with an attribute dialog box and asked to provide the name of the feature and the type of feature selected from a drop-down list. In the case of creating a line feature, the Attributes Assistant will automatically calculate the length and the beginning and ending coordinates. After a feature or a series of features is created, the user can run a script to convert the feature into a non-spatial task assignment that is linked to the spatial feature through the feature name. Thus, if you choose to repeat an assignment, you will not need to create an additional feature, just merely link it to the feature that was previously created. For hasty tasks, this tool will utilize predefined text, which is also editable, to help facilitate quick generation of tasks, using attribute information to populate the predefined text. For example, by taking the name of the feature. If it's a line feature, it takes the distance and the beginning and ending coordinates to populate regions within predefined text and store that in the attribute dialog box, and that becomes the assignment for that task. After a number of assignments have been created, the user will want to generate task assignment forms, maps, and GPX files for upload to GPS that constitute the assignment, and a Python script is provided to automate this production. Upon running the script, 3 files are created and stored in a pre-designated folder within the incident directory. The task assignment form, or ICS 204, which is a PDF form consisting of numerous data fields, is populated from information stored in various attribute tables, thus eliminating the need to repeat data entry. And because it maintains its functionality as a PDF form, any information can be further refined as needed in order to meet the planning and operational demands. A task assignment map is also generated along with the task assignment form. This map is created at a user-defined scale that can be customized for the task. The assigned area is automatically centered on the map, and the boundaries of the search area are highlighted. The task map also contains a variety of additional information to ensure the safety and operational capabilities of the field team. Included around the border is both longitude and latitude and U.S. National Grid, or UTM. And these grids can easily be modified for use outside of the U.S. A map name is also included along with the mission information and task and planning numbers and date. Along the bottom is the U.S. National 100,000 K grid designation box based on the IPP, based on the location of the IPP, along with the UTM region. And finally, IGT for SAR includes an algorithm to accurately calculate the magnetic declination based on the location of the IPP and the current date. This information is also included in the incident information attribute table. And finally, a GPX file is created for the assigned area for upload to a GPS for use in helping to ensure searchers are searching in the desired location. All 3 of these elements are generated for each desired task when the create assignment form is executed. Once the search effort progresses beyond the hasty and quick response task phase, oftentimes we end up with the need to search large geographical areas. This is challenging when resources are limited and time is critical. In a few slides, I'll discuss the tools available within IGT for SAR that provide suggestive information that can be used to prioritize the search area and allocate resources. In doing so, we can develop regions of probability that are based solely on where you think the subject is. These regions are prioritized by assigning a probability of area, or POA, that indicates the likelihood of the subject being contained within its borders. In order to continuously assist with prioritizing the area and monitoring progress of the search effort, you need to track the impact of the search effort through the probability of detection on the assigned POA for each region, as well as the rest of the world in the case that the subject is not within the designated search area boundary. For those of you not familiar with search theory, this may sound complicated. And even for those of you familiar with search theory, you may have shied away from it because done manually, it can prove to be daunting. But its advantages are clear, and with regards to efficient and optimal use of resources. And once an initial POA is assigned, IGT for SAR takes care of all the math by the user merely reporting POD based on field team assignments or field team assessments and GPS tracking. Because they are based on the behavior of the subject, probability regions are oftentimes too large for a single team to adequately search in a timely manner. Thus, regions are typically subdivided into searchable segments, With regard to search theory, POA applies to the probability regions, while POD applies in the search segment. So it's critical to maintain a link between search segments and probability regions in order to monitor adjusted POA and track progress. IGT for SAR does this by providing an intimate link between regions and segments. Without having to manually redraw the segments from regions, IGT for SAR has a built-in tool that copies the regions along with various attributes into the search segment feature class. The user can decide if they want to further subdivide the segments into smaller segments for searchability. But as the segments are contained within the region, it is possible to relate activity that occurs in the segment back to the region, even if the segment is further subdivided. We will see this in more detail in the video tutorials that cover search theory. As I previously mentioned, in order to adjust POA, we need a method to track search effort. Probability detection provides a quasi-quantitative value for doing just that. POD is a team's estimate for the likelihood that they would have found the subject had the subject been in that assigned area. POD is typically based on field team member estimates after the search. Unfortunately, data has shown that even trained searchers are poor judges of how well they've searched an assigned area. To address this challenge, I've included various capabilities that make use of recorded GPS tracks. In addition to being able to display the tracks directly on the map, showing where the teams have searched, it is also possible to use the tracks to estimate a theoretical probability detection, or POD, based on the area covered. To determine the area covered, IGT for SAR considers the size of the team and their reported average spacing. Using this information along with the GPS track, the area searched is determined. Comparing the area searched to the area assigned, it is possible to determine a theoretical POD. And because GIS can easily follow GPS tracks across search segments, it is possible to credit teams with searching outside of their assigned areas. This provides a more accurate picture of the area search compared to just post-search debrief estimates. Continuing with the theme of tracking progress, IGT for SAR incorporates predefined colors and fills in order to graphically display the status of a particular search area and the number of times it has been searched. Similarly, predefined symbols are provided to track the status of field teams. And although the current version of IGT for SAR does not utilize real-time tracking of resources, the capability exists within ArcGIS and is planned for inclusion in future versions of IGT for SAR. Similarly, we can also track clues and introduce the use of pop-ups for quickly displaying of information. Furthermore, IGT for SAR installation includes an Excel spreadsheet that mimics the layout of the SAR default geodatabase. Using the XY loader functionality within ArcGIS, someone running Microsoft Excel, Google Docs, or some similar type of spreadsheet software can record clue information, which can then easily be absorbed into IGT for SAR and ArcGIS for display. As I previously mentioned, we can also use IGT for SAR and ArcGIS to assist with communication planning across a search area, as well as assist with cell phone-related investigations of missing or lost persons. I've included a number of data fields within various feature classes to accommodate this type of analysis. We've all heard the saying that a picture is worth 1,000 words, and that also applies to relaying incident objectives or incident action plans. As opposed to merely describing our objectives for the next operational period, we can display those objectives graphically. Furthermore, by displaying the objectives in GIS, we have the added benefit of the analytical capabilities built into the software. For example, we can now measure the size of our objective as opposed to only providing a qualitative description of the area we want to search. This has the added benefit of helping to estimate resource needs for future operating periods. IGT for SAR includes a number of pre-built map layouts for various needs ranging from field maps to briefing maps and situational updates. Using some of the built-in functionality of ArcGIS and IGT for SAR, you can easily switch between layouts with a simple click of a button. My last topic in this IGT for SAR overview will be to discuss some of the functionality related to modeling to assist with planning and analysis. SAR incidents are fraught with uncertainty, and whatever can be done to reduce some of that uncertainty will hopefully lead to finding the subject quicker. Some of the uncertainty can be lessened by having a better understanding of how the environment and terrain may have influenced the behavior of and decisions made by the missing subject. As stated earlier, this helps in prioritizing the search area. In helping us analyze the situation, GIS allows us to play out a number of scenarios to help us evaluate their likelihood. We can also consider the possibility of conflicting clues to help us rationalize what is possible. For example, in comparing a canine alert and a possible sighting that occurred close to the same time but in different locations. This leads to a better understanding of the assumptions we make and the overall uncertainty. In the past, we've considered the theoretical search area, and oftentimes we disregard it because it encompasses such a large area. Basically, the theoretical search area assumes that if a subject had been missing for some period of time and could walk at the same speed in any direction, how far could they have gone? In this example presented here, we consider someone that had been missing for 1 hour with the ability to walk at a speed of 1 mile an hour. Using the described method produces a search area of over 4,500 acres, just after 1 hour of the subject being missing. But in reality, we know that in wilderness environments, it is unlikely that someone can maintain the same speed regardless of the direction they went. We know that some walking is typically slower when traveling uphill versus across flat terrain or level ground, and it's usually a lot faster to walk along a trail than it is to walk through thick vegetation. Without a GIS, it would have been difficult to include the impact of terrain and environment on theoretical search area. But now, with the availability of detailed remote sensing and vector data, it is possible to estimate a cost surface and least path model based on the impedance imposed by the surrounding environment. This mobility model that is built into IGT for SAR provides the ability to account for access to travel aids such as roads, trails, utility right-of-ways, etc., land cover, slope, and travel barriers such as streams of various size, in order to estimate how far someone could have traveled across the terrain in the search area in a given amount of time. Using this model, along with the same walking speed and time we showed in the previous example, we were able to reduce the theoretical search area from over 4,500 acres down to just 200. And IGT for SAR includes other types of models based on data reported in Bob Kester's previously mentioned text on lost person behavior. Many of these models have been automated by relating the information back to the subject category as reported in the subject information. And we'll see more examples of these various models in some of the video tutorials. In summary, GIS provides an excellent framework for planning, analysis, and operational management of wilderness search and rescue operations. IGT for SAR combines the ability of relating spatial and non-spatial information, provides numerous tools and data layers to help automate the workflow, and provides a host of tools to provide suggestive information to help prioritize the search area. As previously mentioned, this is an introductory video that was intended to help pave the way for a series of video tutorials on the use of IGT for SAR. What will follow is a collection of videos, each focused on a different aspect or capability of IGT for SAR. Each video will build upon the previously discussed elements and should offer the end user a better understanding of the workings of IGT for SAR. So stay tuned for additional videos, and thanks for your interest in IGT for SAR.